Okay, okay, guys, can see the document, right? And hi, everyone, can see the document?
Yes.
Okay. Okay, so let's start our lesson today. So, we already started electromagnetic induction yesterday. So we talked about what is meant by magnetic flux. So what is flux? Magnetic flux, the product of magnetic field strength normal to the plane of the surface and the area of the surface. It's your magnetic flux. Weber. So you got magnetic flux linkage, just magnetic flux B dot A cos theta, because the angle given must be vertically that angle. Okay. And linkage means just times the number of turns. More turns, flux linkage increases. Then we talk about the two laws. Okay, first, we talk about Faraday's law. Faraday's law says what? Induction, electromagnetic induction says that the induced EMF is directly proportional to rate of changes of magnetic flux. Okay, they say EMF is d psi over dt. Of course, psi is what? B dot A dot N. B dot A dot N. Okay, you want to get a greater EMF from a generator, try to have a strong magnet at the side, try to have a big area, the coil you use, try to have a bigger area possible, try to have a strong magnet, okay, at the side, and of course, try to have a more number of turns, okay. The coil must have more turns. Have a turn like this, you can have another coil here, you can have another turn here, you're full of turns in every direction. It drives the EMF. And of course, the rate of changes of flux. The time to change that flux must be very short. That means the water or the wind or the nuclear reactor, which that energy is used to push this turbine, must be huge, so that the time rate of changes of flux become greater, so you get a big EMF. Okay. Okay, so let's be continue today. Today's lesson. Okay, so we talk about Faraday's law, we talk about Lenz's law. The day, I think, towards the end, we talk about Lenz's law. What Lenz's law said? There are directions induced EMF to cause the effect to oppose the change producing. Okay. The wire, when cut by the magnetic field, the wire will induce the EMF. The direction of the EMF is such that to oppose this change. Okay. That means if magnet north pole approaching the coil create a magnetic field such that on top will induce a north pole also by the coil. Okay, so that repel. Okay, when the magnet going away from the north, going away, so the coil will induce an EMF in the other way around, so that the top induces what? South, to pull it back. So we want to prevent the movement, inducing it. Okay, so based on conservation of energy. Okay. Now you see one question here. So there is a pole of 0.08. The area is 6.5. It has a 255 turns, 250 turns. The coil is withdrawn from the field in time 0.26 seconds. That means you have a magnetic field. Sorry. So you have a magnetic field. Okay. The coil was inside that magnetic field. The coil was totally removed from the magnetic field, totally removed from the magnetic field. They're asking what is the EMF induced in this coil, how much? So the flux change is how much? What is EMF induced? D psi over dt. Or in other words, you don't like to put the D, changes of flux over changes of time. Okay. So final flux minus initial flux over time. Cambridge, they like to put the final flux minus initial flux as a modulus. They want to make it always positive on top. So make sure always on top become like positive. No need put negative because real equation got negative, right? Cambridge, they don't really, when calculation, they don't really put the negative. They just want the magnitude. So you just give a positive answer. Okay. So you see the working now? The magnetic flux change is how much? Got maximum flux B dot A cos 0 because 0. We assume the magnetic field is perpendicular to the surface, so theta is 0. So this is the original magnetic field, magnetic flux 5.2 times 10 to the negative 5. So what is the change in flux? Final flux becomes 0, right? Final flux becomes 0. Minus initial flux is how much? Is this the initial flux? But multiply by the number of turns, you get a flux linkage. Okay, then you get that changes in flux. So negative. You actually, as I said, you want to stick with the final minus initial, you got a negative answer. But when you calculate the EMF, right, just put the changes in flux as positive. Just want the magnitude for the EMF. So changes is 1.3 times 10 to the power negative 5. We put it positive over 0.26. We got 0.054. Okay. So yeah. So normally I wrote here d flux over dt is actually n d flux over dt. The flux is actually b dot a, n times b dot a. N must be outside normally. So we wrote like n d psi dt. Negative. This is the proper way of writing the EMF. Okay, normally n is not included inside the flux. That's flux. Flux is b dot a only. So you put the n outside. Okay. Okay, any questions from here? No questions. Okay, now your turn. Okay, let's implement the idea. Okay, you see there is a coil here. It has a 30 turns, 10 centimeter, 12 centimeter, 2.5 Tesla is applied here. Calculate the average induced EMF in the rectangular coil if it's moved out of the magnetic field. Okay, this coil, they entirely move out from the magnetic field. What is the average EMF induced? You calculate for me, 1 minute. The coil is inside the magnetic field first. Find the initial flux. Then when it removed totally from the totally from the magnetic field, the flux become how much? And the coil is totally removed from the magnetic field, flux become how much? Becomes 0, right? The final flux becomes 0. Initial flux is the B dot A here. B dot A. Then the changes you must multiply by the number of turns. Do you have number of turns? 30 turns. Okay. So the changes in flux linkage totally you can put together with n. So 0 minus NBA, right? Over the time taken is how much? Time taken is 0.5. Okay. Flux, final flux minus initial flux. But as I said, the top value you always take it as a modulus, like take it always positive. You have a 0.5, we got the answer. Okay. So hope your idea in your mind. Let's do the work. Check the working at the other slide. No need to do, but hope the working I'm going to show That working is in your mind now. Okay. We go to A. So this is how the answer should be. EMF is negative d psi over dt, changes NBA, final minus initial negative, so you get the 1.8. But as I said, if your exam, your A level, they're going to write like this. EMF is, they're just going to put flux over time. The flux, right? They're definitely going to put final flux minus initial flux, but they're going to take it as a modulus over the time. Over the time. So you don't need to put modulus. You just take it, the flux change as positive always. So I put MBA minus 0 to make it positive over time. Get the answer. You will get 1.8 volt also. Okay, this is what the Cambridge working will be. Okay, you want to follow this style? This is, I can say it at the university level. This is the actual way of doing. You consider the negative, the flux always final minus initial, then you get that answer. You want to follow this method? Also can, more proper way. But I tell you lah, don't get confused when you see mark scheme. Mark scheme, they always put the flux as positive. And the EMF, right, they won't put negative in front. Okay, some simplification. Okay, any question from here? Okay, I prefer you use the Cambridge one. Use the Cambridge one. Just make the flux always positive. Okay, so you get a 1.8 volt. Any question from here? Okay, I go back. So this coil, when it was removed totally from the magnetic field strength, the coil H going to induce 1.8 volt at the H. Okay, because it's a closed loop, current will be initiated. So current will start to flow. Now my question is, extra question for part A. Use Lenz's law. Tell me, the 1.8 volt induced in this coil will initiate the current to flow clockwise or anti-clockwise? 1 minute for you. The 1.8 volt which is generated in this coil and was totally removed from this magnetic field will make the current flow in this coil clockwise or anti-clockwise. Okay, how to find? Use Lenz's law. What Lenz's law said?
Opposite.
Yeah, the Lenz's law said the EMF induced is such that it opposes the change which produces it. You tell me what type of change happens here when you move this coil going out from this magnetic field? Anybody? Flux rising or flux decreasing?
Moving out.
When the coil moving out from this magnetic field, what type of changes happen? Flux rising or flux decreasing? Yeah?
Flux reducing.
Flux reducing. So the current in this coil must move such a way that it must increase the flux. How it can increase the flux? Create a magnetic field, same direction as the original magnetic field, or oppose the original magnetic field. Anyone? The flux is rising, so the current must flow such a way that to increase the flux. To increase the flux, you need to strengthen the original magnetic field or oppose the original magnetic field.
Strengthen.
You must strengthen the original magnetic field, right? So use your right hand grip rule. Your thumb must point where? Into the page. Point your thumb into the page and check your finger, which direction your finger is showing. Clockwise or anti-clockwise?
Clockwise.
So it's clockwise. So the current should flow this way. Like there is a 1.8 volt battery was generated at this age. Okay. Then the current will initiate in a clockwise direction when you move this coil away from this magnetic. Okay. Any questions, guys? So those who found the current should be clockwise, good. Understand which direction to show the current. Use Lenz's law. Okay.
So
Now,
using the right hand rule, the thumb is supposed to be the north pole, right?
the thumb pointing towards the North Pole.
Yeah.
Okay. Okay, so that's the A. A. Okay, now look at the B. Okay, the rectangular coil in A is moved back to its original position. Just put it back like they just put it back here. Now what they do, if the magnetic flux density decrease from 2.5 to 0, now what they do, they never move the coil. The field strength they change. The field strength they change from 2.5 drop to 0 in 0.8 seconds. Calculate the average induced EMF in the coil now. Okay, how do you do this? Okay, so how do you do this? The magnetic field now, which is strong 2.5, drop to 0. So tell me, the flux of the coil dropping or rising?
Flux.
2.5 becomes 0. The magnetic field, so flux is dropping, right? Flux, from higher flux, it dropped to 0 because magnetic field becomes 0. No flux here anymore. So flux is dropping. So do coil induce EMF? Yes, the coil will induce EMF. Why the coil induce EMF? Because there is a magnetic field change. If magnetic field change means the flux is changing. Flux is changing to the coil. Because the coil experiences flux change, according to what law? It's going to induce EMF? According to Faraday's law, it will induce EMF. So EMF is generated. So how do you find the EMF? Again, changes in flux over the time. Changes in flux, in this case, we want to make the top value positive. So final minus initial, initial minus final, good. I go follow the Cambridge one. Because final is 0, so I go here, initial minus final. I want to make the top positive because initial is I over the time. The initial flux is how much? B dot A dot N over the time. B how much? B is of course 2.5. A is how much? A is the area, the surface area here. So 12 times 10 change to meter. Then N is how much? N is 30 ton. So I'll get the time how much? Time to change this magnetic field 0.8. So I'll get the EMF. Okay. So yeah, the B answer will be like this. On B1. As I said, this is the proper way of doing lah, but I'll show you the flux. It's just the changes in flux linkage. The changes in flux linkage lah, before and after. Must make the flux linkage positive over time. You will get 1.1. Okay. Okay. Any questions? Part 1? Make sense? Okay.
Teacher, how do I calculate the area for the wire?
Area of the wire. This area, this rectangular area.
Why is it the rectangular area? Isn't it the wire? Wire isn't it cylindrical?
No. The wire covered by the coil. How much of flux it capture inside it?
Still works, right? Like,
Yeah.
like, it still works like a cylinder, right? Like circle area and rectangular area.
It should be a rectangle because in this case we didn't turn it. We never turned this coil, you know.
Oh, yeah.
We just, if you turn it, then it becomes cylinder lah. Like a pivot here. You turn it, then it becomes a cylinder. This one just the magnetic field strength on top of it, we weaken it. That's it. So the area is just a rectangle. Okay. Not the area of the if you have only one wire, if you have only one wire, okay, let me do this. Okay, let's say you only have, this is okay. Okay, if you have only one wire, and this is magnetic field, okay. Let's say this wire, this wire length is, let's say, 10 centimeter, 10 centimeter. You move this wire this way, and finally you put this wire here, and the horizontal length you drag another 10 centimeter. Okay. So what is the EMF induced in this wire? Okay. What is the EMF induced in this wire? So flux change over the time, right? Let's say it move for a time of 0.5 seconds. So you put down here 0.5 seconds. Flux is B dot A. Okay, which area you going to put? Is it the area of the, do you need the diameter of the wire? The area, the cross-sectional area of the wire? No. The area it swipes. This area, the rectangular area. So the area you're supposed to put here is the area it swipes. So it should be 10 times 10. Change to meter. Okay, the area it swipes. That's the area for this one conductor. If the conductor is in a rectangular, then the area we use is the area trapped by this coil. Okay, not the area of the one conductor, cross-sectional area, the area trapped by the wire. Okay, Shiki, good idea.
Okay, thank you, teacher.
Sir, another question. Is the area of the coil, well, the coil itself, the inside the coil, or is it the area of the magnet that is perpendicular to the magnetic field?
Area of the coil.
No, not perpendicular to magnetic field. I mean, like, is the area inside the coil, or is it the area of the magnet that is going into the coil?
The area of the coil.
Or the coil.
The area of the coil. Normally they will give magnetic field like this. Normally the magnetic field will be what do you call?
Large.
Greater area than the coil normally.
Also, that means that even though it's small magnet, but the magnetic field is high, so it doesn't really matter. The magnet is small.
Yeah.
Like the magnet, not the magnetic field. I mean the magnet itself. Yeah.
Actually, you see, you are asking. Let's say you have a coil here, magnetic field only this region.
Yeah.
This is your magnet. So then, which area to be used, right?
Yes. Yes.
So in this case, B dot A for this area you have to use. This area you have to use. B dot A. No, you can't. You have to use this small area. Sorry.
Oh, small
But
area.
only the small area. But normally this never happen. Normally they put the magnetic field region will be wider than the coil.
All right.
Okay, so B1, we able to calculate the EMF, just the flux change over the time. Okay, now extra question. Tell me now, okay, for the B1, the current will flow clockwise or anti-clockwise? Use your Lenz's law and use your right-hand grip rule. Tell me, the current will be clockwise, anti-clockwise for B1?
B1.
The flux is dropping or rising?
Dropping.
The flux is dropping. So according to Lenz's law, it opposes the change. So you need to rise the flux or decrease the flux.
Rising.
So it rises the flux. So how you can rise the flux? Produce the magnetic field, same direction as the original one, or oppose the original one.
I mean, it's not moving.
But flux is changing, right?
yeah.
Flux is changing. So according to Lenz's law, Faraday's law, EMF will induce. According to Lenz's law, the direction of the EMF will such that to oppose the change. What change happens here? Flux is rising. Flux is rising or decreasing? Sorry, flux is decreasing. 2.5 becomes 0. So according to Lenz's law, it need to oppose the change. So it tried to rise the flux law, right? How we can rise the flux? By creating a magnetic field, same direction as the original or oppose the original one.
Oppose.
Because flux is dropping, you want to rise the flux. To rise the flux, you must create a field, same direction as the original magnetic field, right? To strengthen it. Okay? So the EMF must induce, the EMF must be such as, the current will flow such as to create a magnetic field into the page again.
Okay.
So if the magnetic field produced by the current into the page, the current will flow in which direction? Use your right hand grip rule. At some point into the page, right?
Clockwise.
Would be a clockwise again. Yes. For B1, the current again flows clockwise. Okay, for the B1 also. So that's the answer for B2. B2. Indicate and explain the direction of the induced current in the coil. Okay, you can say that according to Lenz's law, it opposes the change. The change happens here is the flux is decreasing, so the flux need to be increased back. Therefore, according to the right hand group, the current should flow in a clockwise direction.
So that means that it wants the magnet to move. Is that correct?
No, the current will flow such that it tried to decrease it tried to stop the change.
Okay.
So the coil won't move. The coil just generate a current. This is a generator already. Generator produces.
Okay. It means still producing current until it becomes zero lah.
Yeah. Until the changes never happen. So when the 2.5 Tesla drop to zero, right? At that moment, 2.5 drop to zero, you will get that EMF. After magnetic field becomes zero, and zero for another few seconds, no current generated. Current only generated when there is a change in flux. Okay. So 2.5 change to zero, you get current. After zero, no current. Okay.
Teacher, isn't it like when the magnet is moved into the magnetic field, right? This motion causes the magnetic flux to decreases from 2.5 to 0. Doesn't that means the the direction of the magnetic field produced by the induced current is opposite direction of the magnetic field?
That's the pole. Pole will be opposite. The pole will be opposite. I know. What you are trying to say is this, right? You are saying like you have a coil here, like you have a magnet on top. 2.5 drop to zero means you move away the magnet. So top you're going to produce north or south? South, right?
Yes.
That's what you're saying. So giving an opposite pole, right? That's what you are. That's your idea, Shike?
No, my idea is because the coil is moved back into the magnetic field, right? Doesn't mean that north pole, the coil also produce another north pole, so it's like two north pole like that. So the magnetic field, the magnetic flux only decreases from 2.5 to 0.
Oh no. The question is the moving part, not the moving part causes the change in flux. They just said they put the coil inside. They already put the coil inside already. Okay, they move back the coil inside already. Now they change the magnetic field strength only. They never move the coil anymore. Understand? They just put the coil not moving anymore.
The first sentence is just describing the initial condition of the magnet, is it?
That's the initial because part A they already move out, right? Part B they just move back in. Now the question starts lah. Now they're changing the magnetic field. That's it. The Coil not moving
okay.
anymore. Okay, guys, so look at the third one, C. Okay, so calculate for me. I already help you A and B. I need to predict the C. The magnetic flux in B is increased to 4.5. Okay, now they increase to 4.5. Okay, now the field is 4.5. Now they do the changes. The changes is now is the coil is rotated for 90 degrees in 0.3 seconds. So the field now is 4.5. 4.5. They never change the field. The field is now increased to 4.5. Okay, so field not changing is 4.5. The coil is turning 90 degrees. What is the EMF induced now? Final flux become how much? When you turn this 90 degrees. Like the center, from the center, sorry. Like center pivoted, it turned 90 degrees. Okay, it turned like this 90 degrees. So final flux become how much? Final flux will become 0, right? Final flux will become 0. Okay, because you turn like a door you flip it for 90 degrees, the door finally become like this. You only see the side door only. So this is the magnetic field. So area we assume 0. Area is assume 0. No area overlapping. So the flux is 0. Okay. So 0.3 seconds. So as usual, see. So again, final flux minus initial flux. Final flux is 0. Initial flux MBA cos 0 degrees, or you just don't need to put cos 0. MBA only now because it's perpendicular. 1.62. So changes in flux over the time, you get your EMF 5.4. Okay. As I said, Cambridge, just go changes in flux, you take it as positive over time, changes in time. Cambridge won't put negative, remember. So this is your Cambridge. Cambridge just going to put flux is EMF is changes of flux over changes in time. Flux linkage, flux linkage. Better put N on top. Flux linkage. Okay. Okay. So yeah, so that's part C. Any questions so far? No questions, Okay. So now this question I skip. I go to this one also. It's easy. I skip this first. I go to this part. Yeah. So EMF induced in a moving straight conductor. So you see this diagram on top. The conductor length is L. It's L. Okay. The conductor move to the right with the speed of V. How much is the EMF induced in this conductor? So flux over time, changes in flux over the time, flux linkage over the time. Here the flux linkage is the B dot A. But A is what A? A is the area swiped by this conductor, the purple conductor. Okay, the area is swiped by the purple conductor. That means the length times the this origin or what do you call horizontal distance. The horizontal distance in terms of speed will be V times time, V dt. Differentiation form V dt. That's why area here put L times V dt. V dt is the horizontal distance is traveled. Speed times time over the time cancels. So the EMF induced by a conductor, just a 1 bar conductor moving, swiping the magnetic field is BLB. It depends on the magnetic field strength, of course. It depends on the length of the conductor. More longer the conductor you swipe, more greater the EMF. That, of course, how fast you swipe. More faster you swipe, more greater the EMF. Okay. And for this conductor, which direction the current will act on this conductor, we use Fleming right-hand rule. Fleming right-hand rule is used for current acting, force acting on a conductor, bar of conductor. So because it's moving to the right, you put your FBI again. If it's moving to the right, your force is to the right. Okay. Magnetic field is into the page. And you check the current, which direction is the current. Okay. In this case, give a try for this bar method. Where's the current going to be? I think the EMF pointing upwards. Your current should be upwards. Okay, you just focus this bar. So your force is to the right. Your magnetic field is into the page dot. I think your current going to point upwards. Current is the EMF, direction EMF, so upwards. Fleming right-hand rule to be used. Very low profile, Fleming right-hand rule. Okay, so current carrying conductor, conductor cuts the magnetic field line. The induced EMF is BLB. Any questions from here? No questions, Okay. Okay, so this is another one question. Okay, lots of wording. Okay, I don't read this. Straight away I go to the diagram, then we can explain from there. Actually, the storyline tells about this trolley. The trolley has a rectangular coil, ABCD, and the trolley is about 5 centimeters away from a magnetic field region. The ABBC as a dimension. ABBC how much? So here region bounded by 5 centimeter mark. So AB is 10 centimeter. BC is 5 centimeter. Okay, it means AB is 10 centimeter. This is 10 centimeter. Okay, and this is BC is 5 centimeter. It's 5 centimeter. Okay, it's going in, and here's the number of turns. The number of turns of this ABCD. The number of turns is how much? Number of turns is how many turns it has? This is number of turns. 20 for ruler time age 100 centimeter. Oh, they don't have number of turns. So. Okay, the trolley move with a speed of 100 centimeter per second. 100 centimeter per second and move forward. And the coil has a resistance of 20 ohm. Okay, that's the whole idea. Okay, you don't have number of turns. The resistance is 20 ohm. And the speed moving forward to the right is 100 centimeter per second. Okay. Okay, now question. State and explain whether there is an induced EMF in the rectangular loop. State and explain if there is a EMF induced in the rectangular loop when it move from 0 to 5. When BC traveling between 0 to 5. Okay, you go back. When BC travel 0 to 5, is there any EMF induced? The BC approaching for 5 centimeter here. Is there any EMF induced?
No.
No. Why? What's the reason?
It's not cutting the magnetic field.
Okay. Or you can say no changes in magnetic flux experienced by the coil. Okay, next. 5 to 10, is there any EMF induced? Of course,
No.
yes. 5 to 10, it cuts, but partially cuts, right? The coil will be like this.
But the circuit is not complete, right? So does that consider as induced current?
Okay, do the coil experience flux change or not?
One part of it will.
But so yeah, if this is the coil, the magnetic field only applied in this region. So it has flux. There is a flux change. Originally, initial flux is 0. Final flux is B dot A. The what do you call? The B is the magnetic field. A this area this area, right? But there is a flux change. Because there is a flux change, there will be a current induced here. There will be EMF induced in this bar on the left. So you're going to initiate a current. You will have a current here. So there will be a current. There will be an induced EMF. Flux is changing, although partially, but it affects the coil. So flux is changing. Okay, so answer 5 to 10 centimeter. Is there will be an EMF? Yes. Why? Because the coil experience changes in flux. The flux is increasing or flux is changing. So therefore, it will induce EMF according to what law? Faraday's law. Okay. Okay, now the question is, how much the induced EMF will be from 5 to 10? So yeah, B dot A minus the 0 over the time. Okay, we come to that later. Okay, now we go to the next one. 15 to 20. Is there any flux change? 15 to 20. So now the coil is completely inside the magnetic field. Sorry, yeah. So 15 to 20. That means the coil is already completely inside. It will reach 15. Then the coil is completely inside, just moving to the right and come to a new location, 15 to 20. Is there any EMF induced? Anyone? Is there is flux change? 15 to 20. Flux change or not? Or no flux change? What is flux? B dot A. And 15, what is the B dot A? So completely the entire area is inside the magnetic field, right? Okay, so the flux is maximum lah. When move from 15 to 20 also, the entire area is inside the magnetic field, right? So the flux, same or different? P dot A. P dot A is same, right? So no flux change. The flux change is 0 from 15 to 20. So there is no EMF will be induced in this coil. Okay, no EMF will be induced in the coil because answer is what? No flux change from 15 to 20. The flux is maximum, but the maximum never change. It always maximum lah. No change in flux. So 15 to 20, no EMF induced.
So that means that the coil is only 10 cm.
Coil horizontally is 10 cm.
Oh, but the region of the magnetic field is
No, hold on.
50.
Coil is how much? The coil length is how much? Length is 10 cm. Yeah.
Oh, okay.
DC, yeah, 10 cm. Okay, so now next 20 to 25. Is there will be any EMF induced?
Yes.
Yes, there will be a EMF induced. Now the coil, which is entirely inside the magnetic field originally, partially come out. Flux is dropping for the coil. Flux is dropping. That means the flux is changing. Therefore, EMF should induced. Okay, now the question is, when the coil enters the field from 5 to 10, from 5 it go to 10, which direction the current will flow in this coil? Clockwise or anti-clockwise? 5 to 10. 5 to 10. That means the second question lah. 5 to 10, EMF will be induced. The EMF will induce in which direction? Clockwise or anti-clockwise? Use your Lenz's law. Tell me. The flux is rising or decreasing? 5 to 10. When the coil move from 5 to 10, flux is rising or flux is decreasing? Anyone? When the coil move from 5 to 10, flux is
Rising.
rising. So flux is rising. So according to Lenz's law, the EMF induced such as to oppose the change. So because flux is rising, the EMF tried to decrease the flux. You don't want the change. So how we can decrease the flux? Create a magnetic field, oppose the original magnetic field or the same direction of the original magnetic field?
Oppose.
Oppose. So your thumb must point out of the page.
Yes.
So which direction your finger shows? Clockwise, anti-clockwise?
Anti-clockwise.
The current flow, anti-clockwise. Okay. coil enters the magnetic field, the current will flow anticlockwise. EMF induced such that the current flow anticlockwise. Okay, until it come to 15, current will flow continuously anticlockwise. But from 15 to 20, no current will be flowing because no changes. When the coil come out from 20 to 25, current will flow which direction? 20 to 25. Current will flow in which direction? Now flux is increasing or decreasing? You come out. Decreasing. So again, Lenz's law, it opposes the change because flux is decreasing. You need to rise the flux. You create a field, same direction as the original direction. So now your thumb point into the page, your current will flow clockwise direction. So you get alternating current. At the beginning, when it enters, current will flow anti-clockwise. When it leaves, the current will flow clockwise. Kind of like the current will flow one direction, then another direction when it leaves. Okay. So this is how the the prediction about the first question. State and explain whether the induced EMF in the coil or not. Explanation. Your explanation always focus to what? The changes in magnetic flux. Okay. You say no changes in magnetic flux. See, there is a change in magnetic flux. Depend. You say the conductor cuts the magnetic field line, therefore it experiences changes in magnetic flux. Therefore, according to Faraday's law, EMF must induced. The direction, you use Lenz's law to explain. Okay. Okay, so B, calculate the EMF. I think it's easy, right? So what is the magnetic flux line from 5 to 15? Going from 5 to 15. From zero flux to maximum flux, right? Entire thing is inside. So changes in magnetic flux linkage over the time, you get the EMF. Yeah. So the flux change, get 200. The entire thing. Okay, I think I don't feel you have a problem with EMF. Just flux change. The big flux minus the small flux over the time, you get the EMF. Okay.
It's just a little bit hard to imagine the direction because of the 2D diagram. Usually 3D is like better to see it.
But so you need to know the direction of the magnetic field, right? Yeah. Okay.
I know that the direction, but I mean like just showing a part of it is hard to know how the motor will move.
Oh, moto, yeah, moto. This is like a one dimension movement.
Yeah.
Okay. Moto is turning. Okay. Okay, we will come to that later. Okay. I'm being understand the one dimension first. Flux increasing, flux decreasing. Okay, look at C. Calculate the power produced in the rectangular loop when the leading edge BC is traveling between 5 to 15. When the leading edge travel 5 to 15, what is the power dissipated? Okay. How do you find the power dissipated? You got your EMF already. Okay. Part B, you know that what is the EMF generated in the loop. So power dissipated and EMF how related? You know resistance. So what formula? P equals to V squared of R to be used. Right. Power. So C on top. Power dissipated in the coil is V squared over R. V is the EMF induced in the coil, flux over time. Just now we calculated in part B, squared over the resistance of the wire, 20. So you get this is the power generated in the coil. Okay. Okay, so that's that's your C. 20 to 30, 20 to 30, the same power will be generated, right? Yes. Flux change the same. 20 to 30. Completely leave. So flux change is the same, so same power generated. Okay. D. Plot a graph, magnetic flux against the loop position X. Now we're going to plot the flux graph, flux versus position x. How the flux is changing. From 0 to 5, flux is 0 to 5, flux is 0. Okay. 5 to 15, flux is rise. 15 to 20, flux become constant. 20 to 30, flux drop back, right? So this is the graph, right? This graph. Okay. This is flux versus distance. The first 5, flux is 0 because the coil haven't overlapped with the magnetic field yet. Then the coil slowly get into the magnetic field region, so flux rising linearly because the speed is constant. Then here the flux become constant, then drops. Okay, guys, I never told you one thing. How they got EMF from 5 to 15? Changes in flux over the time, right? How they got the time? Time they got it from the speed, right?
Yes.
Speed times the distance lah. How long a distance it traveled from 5 to 15? 10 centimeter. So how do you find the time? So V equals to distance over time. So you can find the time is distance over V lah. Distance 10 centimeter divided by 100 the speed. You get the time it traveled from 5 to 50. Then the time is used to find the EMF lah. EMF is flux change over the time, right? You can put the time lah. D over V is your time here. Okay. You find the time for the EMF. Okay. So this is your flux change. Okay. Now we're going to find how EMF is induced. Which direction EMF induced? How EMF and flux related? How EMF and flux related? EMF is negative d psi over dt. Okay, d psi over dt. Again, I can share this relation analog to acceleration and velocity. Acceleration is dv dt. I can analog to this. So the flux you imagine like velocity. In the EMF you imagine like acceleration. But negative. So negative means what? The flux above graph, right? You imagine like velocity. You draw the acceleration graph. How's the acceleration? If this is a velocity graph, your flux imagine like velocity now, analog like velocity. Draw the acceleration graph for this. So when velocity constant, acceleration is 0. When velocity is the gradient is positive, acceleration will be what? Positive, right? Constant. When velocity constant, acceleration will be 0 again. Okay. When velocity dropping down, gradient is negative, acceleration is negative. The graph will get like this. The one I am putting in the red ink. Graph for acceleration will be like this. But because negative, now consider the negative. Because EMF is negative, so you reflect the graph in x-axis. So your final graph will be the up positive, then to become down, and down negative square will flip to upwards. Okay. So your EMF graph will be like this, square. Okay, do you understand flux to EMF? Very common, they last flux to EMF. You have to know. Okay. Okay, let's do more about this one. Okay, just one. Just another 1 minute. We stop here. Okay. So what? EMF is negative d psi over dt analog to acceleration dv dt. If your flux change like this, going up, how's the EMF going to change? So imagine your flux like what? Like your VT graph, like a VT graph going up. How's your acceleration graph going to be? Curve up. So acceleration graph going to be a straight line with the constant gradient, right? Okay. So how's your EMF graph going to be? EMF graph is negative because it's negative. It's negative. So this graph you have to reflect it in x-axis. So how the EMF graph going to be? EMF graph going to be directed like your T as your mirror. So this graph going up, so your EMF time will go down. So this answer. When the flux is going up, EMF is down, negative. Okay. Okay, now I'm asking you more. Flux is a sine graph. EMF will be what graph? Flux is a sine graph. EMF will be what graph? Sine, negative cos, cos. So how do you do? So your flux, you can imagine like velocity. How do you get acceleration? Velocity is a sine graph. Acceleration will be what graph? Anyone?
Cos graph.
So you differentiate, right? Acceleration is dv dt. Differentiate v. Differentiate sine, you get what? Cos. So the acceleration graph going to be a cos graph. So EMF going to be what graph? EMF is negative one. So you need to flip this cos graph, right? In x-axis. So it become what graph?
Negative cos.
Yes, it become negative cos. It's a negative cos. So flux change to EMF, thing like velocity change to acceleration. But after you get acceleration graph, you have to flip, you have to reflect it in x-axis, you get the EMF. Okay, so homework. This one homework here. Go back to the Word file. There is 2 questions here down here. Your current graph given. You need to find the flux graph, EMF graph. Okay. Try to figure out these 2 graphs. And you have another question. Current graph given. You draw magnetic graph. You have to draw the EMF graph. See here. Flux is B dot A. B is what? Inside B got current. Inside B, because B is proportional to current of the conductor. Okay. So if current is sine means magnetic field will be what shape? If current is sine, changing sinusoidally means magnetic field will change sign, right? Same pattern one. Because current affects the B, proportional. So if I change sinusoidally means sign, B also change sign. B proportional to flux. So B sign means flux will be what? Flux also will be sign. So remember, current, magnetic field, flux, the shape of the graph is always same because they are affecting each other. They are proportional. So think about I graph. This is how the I change in the conductor, how the magnetic field change, draw the EMF. Okay, any questions, guys? Today's lesson. These are the 2.
Teacher, I have a question.
Yeah.
If there's a long solenoid, right, around 20 centimeter long.
Yeah.
And then I put a magnet inside the solenoid, and I move back and forth in between the solenoid. Will there be any current?
We have,
It doesn't go out of the solenoid. It just move in and out in between the solenoid.
oh, you have a big solenoid,
Yes.
20 centimeter.
And then the magnet is around 5 centimeter like that. Then it moves back and forth.
Back and forth.
Yes.
So you go back and forth. The entire field just here inside there. No change in flux. Flux change is 0.
Then there won't be any current, is it?
There won't be any current. Okay, there should be, hold on. Flux change is, yeah, no flux change, but flux change, only the flux is changing when it's here. Field line changes because the field line flux change. No, cannot be. No change in flux. Okay. Yeah. Good question. Should not, because flux is B dot A. The area is so big. The B is just inside, the entire B inside. It's just moving front and back. The B also never change. So the B dot A will be like constant.
Then if teacher, let's say when the magnet move from left to right, doesn't there won't be a magnetic field induced in the current to resist the direction, the movement of the magnet towards the left, towards the right, and then induce another current?
You have a coil like this, too small, and the magnet is huge, north south, go in, oppose. Okay, if you have the coil is so huge, the magnet is going inside. Magnet is going inside. But here the conductor is huge, the magnet is small.
Then when the magnet move down, then won't the other end of the coil induce a EMF to attract the magnet to prevent it from moving?
If you have a battery, you have to put a voltmeter here or ammeter here. Okay, the very long one. And you put a magnet inside. You put a magnet. When you approaching, you will get voltage. You get voltage increase. Okay, a voltage, yeah, increases. Yeah, correct. When it's the magnet, when the conductor is inside, when the magnet is inside, okay, when magnet is totally inside, flux change is 0. So when let's say this is the 20 centimeter, the magnet is only 5 centimeter. So when entire thing is in 5 centimeter, when you go down, but the entire thing is still inside the coil, the voltage induced is 0. No voltage induced because no change in flux. Flux is 0. When it leaves, then there is a flux change, you get voltage back. So lots of question asked in past year like this. There is question asked past year. They drop a magnet, a small magnet, pass through a huge coil. They ask you to trace the graph of voltage, how the voltage graph produced. Okay, the voltage graph given like this. Okay, the voltage graph given is like this. Oops, sorry. The voltage graph given for that movement is like this. Like this, come down like this. So there is a region where voltage is 0. At this condition is the magnet is totally inside the coil. Totally in the coil. No flux change, no EMF. Only when it about approaching this is part where it's entirely slowly get into the coil, voltage will be induced. This region is the coil is started to come up from the coil, then voltage will induce in opposite direction. Okay, so the coil is big, magnet traveling inside, and it's totally inside the coil, flux change is 0, so EMF induced is 0. Okay.
So is that given that the coil doesn't have significant gaps between loops?
Okay, now question is, why EMF must be 0? Because no flux change. Flux never change. Flux not change. What? B dot A is always constant for this case. Okay, the magnet is too small. The magnetic field is covered in the big area. So the B dot A is like just now the rectangular coil, the trolley. An entire thing is inside the magnetic field. The area B dot A is constant. Here also the B dot A is constant. So flux never changes. So no EMF induced. No EMF induced. Only when leaf got EMF. Because reason we said no flux change inside. Okay, think about this. The next class we will continue again. Okay, try to refer to your notes and everything. Okay, try to visualize. We can discuss back the next class. Okay, think about it. Good question. Okay, this is when inside no flux change. You can see some exam trial papers. The one I listed. You see some magnet question. They will ask like dropping down inside. How's the voltage graph initiated? You see the graph. You should know. Flux change inside is 0. Okay. So we will continue if you don't understand next class. Have some what do you call revision first. Okay. Stop here.